All right, welcome. This is the module 7 in the tech book, or the unit C and D by the district test, or it is chapter 4 and 6 in the textbook. This is basically the review sheet solution that I assign. Okay, here in this video, I'm covering page 3 and 4, which is starting on questions part 8 through the end, which is part 14. All right, so you have the first one here. The triangle to the right is a scalene triangle. Doesn't really matter, but we know that there's no parallel lines here. Okay, we look like there's some internals and exterior angles here. So let's just write that just to make it a little bit easier to look at. Okay, so here this looks like it's on the inside. So this is probably an interior. This is an interior. I just wrote int for interior, and I is also an interior. B here, which is outside, so that is your exterior. E here is also your exterior, and J here is also your exterior. Okay. All right. So we would say would you say angle D is equal to G? No, because it says scalene triangle. Okay. Angle D and angle G might work if it's like one of these. Let me show you. Right. How about something that looks like 30, 30, and this is like 120. Okay. It would work for something called I think this is called an isosceles triangle, but it's not this case, right? So we would so D is not equal to G. We would say that D plus G is equal to J. Let's look at that. Angle D, angle G is equal to angle J. There's these two interior angles, which is opposite to the external angle. Would that be right? Yes, that's actually one of the core concepts that we got. The interior plus this interior does equal that exterior. So that is a valid answer. Okay. B, this exterior, let's see. B is right here. This exterior, does that equal to D? And I? It would be this. It would be has to be its opposite. So this is wrong. What would have been correct was B would be equal to G plus angle I. That would be true. But they had D here. That's why this is wrong. Okay. Is angle J equal to E? J and E? No. It would have to be parallel for it to be the same, but it's not. Okay. Let's look at the next question. Which of the following statement is always true about vertical angles when parallel lines are cut by transversal? So here you go. Here are your vertical angles. Would the sum of the vertical angles be 180 degrees? We have 40 here, 40 here. These are vertical angles. Would the sum be 180 degrees? No. 40 plus 40 is 80. It is not 180 degrees. So that's never true. Sometimes, but not always true. Vertical angles are congruent because they are reflected from each other. We reflect 40 on this side. We reflect 40 to this side. Some of you want to see like the line of reflection. So there you go. That was your line of reflection. So yeah, that looks good. Are the angles in a vertical pair congruent? So I gave you an example here, right? So yeah, acute. I don't know if you guys know this. It's just mean the angle has to be less than 90 degrees. So this is acute. This is acute. Are they? So this is acute. This is acute. Okay, but 105, that is obtuse. Okay, are the angles always acute? No, sometimes they are right here, but sometimes they're also obtuse. So that would be wrong. Next, the vertical angles are not supplementary to each other. Are the verticals or angles, are they supplementary? No. 105 is not supplementary to 105. Okay, they're the same. Okay. Next, determine whether or not each relationship represents a function. So A, vertical line test because it's on a graph. Line draws straight down, passes through 1 point, passes through 1 point. We would say that is a function. B, mapping diagram. We applied the vending machine. Okay. Press a -2, you get a 1. Works. Press 2, you get a 1. Works. Okay. 2 buttons here can get you the same thing. And 0 can get you an 8. Yeah, that's a function. Okay. You press a 1, you get a 5. Perfect. You get a 5, you get a 1. Press a -5, you get a -1. Works. You press a -1, get you a -1. Perfect. That's also a function. You could also put this in a mapping diagram if it helps. Here, chart format. Same thing. No x value repeats, right? So apply the vending machine. Press a -3, you got a -11. Press a 0, you get a 5. Press a 3, you get a -1. Press a 6, you get a -7. Press a 9, you get -13. Nothing breaks, so it's a function. So all these are basically functions. This was part 10. Let's look at part 11. These are all graphs, and you're just looking to see which one's a function. So apply the vertical line test. Draw the line straight down, crosses through 2 points. It is right here, 1 point, another point, and we would say that this one is not a function. This one, draw a line straight down, crosses this point, crosses through this point. That is 2 points, so we would say that is not a function. Draw a line straight down, it only passes through 1, so we test it again. Passes only through down 1 point. We would say that is a function. This one, draw a line straight down. It passes through what point? This point. Passes through this point. We would say this one is not a function. Passes through 2 points. Okay. And here we are given these functions and we were asked to classify them to see if they are linear or nonlinear. So let's review the core concept to determine whether it is linear or nonlinear. 2 criteria for a function to be linear. The first one is the exponent has to be 1, not greater, or nothing less. And there can only be 2 variables like x and y, and it can't be together like x and y. Okay, it doesn't always have to be x and y. It can be like r and t, u and v. Okay, so the first one, the exponent here, what is the exponent here? It is 1 and 1. So yep, is it just x and y? Yep, so we would say it's linear. The x is on top, right? That is the exponent of 1. This is an exponent of 1. That is also linear. This one, it's x and y, but notice this is on the bottom. This, because it's on the bottom, the exponent here is actually not -1. Okay, or if you want to think about it, you can multiply this by x. It becomes xy is equal to 4 plus 2x. Okay, not a function. Next one, 1/3 x is equal to y minus 1. That is a function because, again, the x is already out here. And that's a y, and the exponent is 1. Next, the exponent here is 2. Do you see that? 2? You see the 2 right here? That's bad. We would say not a linear function. Next, x and y. Good. The exponent, is it just 1? Yep. It looks like it is 1 up here, 1 right here. So yep, that would be linear. Next, nonlinear, because look at the exponent. It's 2 right there. That's bad. All right. Remember, make sure you understand there are 2 criteria. So which functions here are nonlinear? Select 2 that apply. The first one, y equals to 3x. Oh, let's review the 2 criteria for it to be linear. It was in the last problem. I'm not going to repeat it. I'm just going to have it here for you to reference. The first one, y equals to 3. That is linear because it meets the criteria. So that's linear. Doesn't work. That's not what we're looking for. We're looking for nonlinear. Next one, exponent 1. You get an x and a y. So that is linear. Next, you are looking for it to be constant. So nope. So let me show it to you, right? Because I don't think I calculated here. Your delta y here is plus 5 here, plus 5 here is plus 5. So you would say it's linear. Next, let's look at your delta y. Delta y here is -1/2. then it goes from here to here, gets you negative 1/4, non-linear. The delta y here is not constant. Okay, this is how we determine if it's linear or non-linear. Okay, is if it's constant. Okay. Next, this would be linear. It has a slope of 0, but it's linear. It's a straight line. And this is non-linear because it curves. Okay, so the two criterias here are when you look at the equation, when you look for the chart, you have to make sure you find a delta y to see if it's constant or not. And if it's a graph, you look at it visually. Does it curve or is it straight? Last one, Mike leaves his house and drives slowly east through the city traffic. When he reaches the highway, he drives east more rapidly until he reaches the shopping mall where he stops. He stops at the mall for an hour. Mike returns home by the same route as he came, driving west rapidly along the highway, then slowly through the city traffic. Each graph shows the distance from home on the vertical axis versus the time elapsed since leaving home on a horizontal axis. Which graph is the best representation of Mike's trip? So I'm just going to isolate a couple of things here. He drives slowly east through the city traffic, slowly, so it's a low slope. Then he drives fast, so it's in green, that it goes super fast, the slope is higher, it's a steeper slope. Then he stops and shops at the mall, so that is a 0 slope, a flat line. Then he westerly rapidly drives along the highway, that is straight down, really fast, down. Then he drives slowly again. So which one would look like that? Okay, each one of the scenarios that is happening in terms of his speed is visually graphed on the individually, and I put it together to create his whole scenario. So this would be B. Okay, there you go. Those are all your solutions.